Okay. So in this lecture, we're beginning to learn some of the basic words and grammar of algebra. You need to speak the algebra language to do algebra. And we start with something which you find everywhere in mathematics, which is the notion of a set. A set is a basic undefined notion for us. We have some intuitive idea of a collection of objects is what a set is. So for example, 1, 2, 17, minus 9, this is a set of numbers. And dog, cat, lion, elephant, that's a set of animals. They're perfectly good sets. And then what's in a set is called an element. So a set contains elements. And the basic notion of equality for sets is two sets are equal if they contain exactly the same elements. So for example, if we have sets A and B, we would say A equals B if A is an element of A, if and only if, that's what this double-headed arrow means, or let's say X is in A, if and only if X is in B. That's what it means for two sets to be equal. And this epsilon, this is the symbol for inclusion or membership. So if we have the set A of 1, 2, 17, and minus 9, we can say that 17, this symbol, this epsilon means 17 is in A, or is a member of A, or is an element of A. So this is some basic notation. If we have this set A, 1, 2, 17, and minus 9, and a set B, which is 2 and 17, you see that every element of B is an element of A. When that's the case, we say that B is a subset of A. So the definition of subset is B is a subset of A if whenever X is in B, that implies X is in A. And the notation for a subset is B contained in A. And we can say A is a superset of B. It's the same as the notion of, it's the same as saying that B is a subset of A. A is a superset of B if X in B implies X is in A. So every element of B, A contains every element of B. And the notation, as you would expect, I think, is A contains B. So this means B is a subset of A. This means A is a superset of B, and they're the same. B is a subset of A if and only if A is a superset of B. Now, to have a good picture of what's going on anywhere in mathematics, it's actually good to be able to draw pictures. And a picture in set theory is called a Venn diagram. So we think of a set as this, everything in this region A. And what does it mean for B to be a subset? It means that every element of B is contained in A. So this would be a Venn diagram that shows that B is a subset of A, because this region is contained in this larger region. Okay. Let me repeat something I said a moment ago. I take attendance by seeing your name when you log into the Zoom website. I look at the list of participants. And if your name is there, I can check you present. But if you are using a screen name, which is doesn't have your last name, I can't identify you. So there are some people who logged in with no, like there's a Liani MS244 staff.
It's Rodriguez, my last name. Sorry about that.
Yeah, no, that's fine. It's just that's the only way I have to see who's present. And now I have you. So that's good. Thank you. There's also a galaxy J7 prime. Is there a name I can associate with that?
It is Evarist Wedrago. I will fix that.
Just 1 second. I just want to make sure I get you down. Okay, so what is your last name, please?
Wedrago. Ouedraago.
Aha, they're Evarist?
Yes.
Yeah, okay, good. Gotcha. Thank you. Is this your first class? Or were you
Yes.
here on Monday?
No, that's my first class.
Okay, all right. No, that's fine. That's fine. I just want to make sure I didn't miss you. Okay, good. Suppose we have two sets. What is called the union of S and T is the set S, and we write this symbol, which looks like a U, S union T. This consists of all X such that X is in S or X is in T, or both. So the Venn diagram, the picture of the union is as follows. Suppose we have some universe, like for example, if we're looking at sets of numbers, this could be the set of all numbers. And here we have a set S. And here we have a set T. And the union is everything which is in either S or T or both. So the union would be all of this. It's everything, if you have the union of two sets, it's everything which is in one or the other or both. And the intersection of S and T is the set S, and this is like an upside down U. It's the set of all X such that X is in S and also X is in T. So in this picture, this is the intersection. This is everything which is in both S and T. So for example, if S is the set 1, 2, 17 minus 9, and T is the set 2, 4, 6, minus 9, and 0, S union T is everything which is in one or the other or both of these sets. So I have 0, 1, 2, 4, 6, 17, minus 9. That's everything which is in one or the other of these sets. And the intersection, what's in both are just the numbers 2 and minus 9. plus 2 minus 9. Okay. Any questions about this? Suppose we have sets S and T. What is called the complement or the difference. The complement of S in T. This is everything in T that's not in S. So here we have S, here we have T, this is the intersection, and this is T take away S. So the complement of S and T is the set which is denoted T take away S. It's like, look at all of T and you take away everything that's in S. That's this intersection, and this is what we're left with. So this is all X in T with X not in S. And this symbol means not in or not an element of. And so if you look at this is S and this is T, this is the intersection. This is everything in T that's not in S. This blue is everything in S that's not in T. And what is called the symmetric difference of S and T is the set. So it's written sometimes with this triangle. This means the symmetric difference. It's everything in S which is not in T, union everything in T which is not in S. So in our Venn diagram, this is the picture. In our Venn diagram, this is the picture. We have the set S, the set T, the complement of S and T, everything in T that's not in S is what's in red. The complement of T and S is everything in S that's not in T. That's what's in the blue. And the blue and the red together is the symmetric difference of the two sets. Okay. Any questions about this? This is really just terminology, but that's what it is. Okay, now there are a lot of set theoretic properties that are fundamental and very important to know because we use them all the time and we use them so often they just have to be somehow written into your DNA in your brain, so you don't have to think about them, you just know they're true and you use them. So here are some properties of sets. So the first is called Associativity. So suppose we have sets R, S, and T. So I could take the union of R and S, that's a set, and I can take the union of that with T. Or I could start by taking the union of S and T, and then R union that. And this identity has a name. It's called the associativity of taking unions of sets. And we also have a similar associativity for intersections. If I take the intersection of R and S, that's a set, and I intersect that with T, that's the same as if I took R and I intersected that with the intersection of S and T. So this is associativity. We also have a property which is called commutativity. This is actually even easier to see. It says if you have any two sets, S and T, S union T is the same as T union S, and S intersect T is the same as T intersect S. So the order in which you take union and intersection doesn't matter. I mean, this is really easy to see because two sets are the same if they have the same elements. Something is in S union T if it belongs to S or T or both. Something's in T or S if it belongs to T or S or both. Those are the same statements. So these sets are equal. For intersection, something's in S intersect T means it belongs to both S and T. Something's in T intersect S means it belongs to both S and T. It's the same thing. That's really all you need is a proof. The third takes maybe a little bit more writing. It's distributivity. It says if you have three sets, R, S, and T, if you take the union of S and T and intersect that with R, that's the same as R intersect S union R intersect T. And R union S intersect T is the same as R union S intersect R union T. So let's just look at an example. Suppose R is the set 1, 4, 7, and 10. S is the set 1, 3, 5, and 7. And T is the set 2, 4, 6, and 8. So R union S is 1, 3, it's just everything in R or S. So 1, 3, 4, 5, 7, and 10. And R union S union T, it's this set plus this set. So I add 2, 4, 6, and 8. I already have 4, that's okay. 1, 2, 3, 4, 5, 6, 7, 8, and 10. And if I take S union T, it's these two sets, 1, 3, 5, 7, 2, 4, 6, 8. That's everything, all the integers up to 8. And if I take the union of that with R, I'm adding 1, 4, 7, 10 to this set. I'm just adding 10. So that's 1, 2, everything up to 8 together with 10. And these two sets are the same. That's just an example of this. Let's look at the distributive law. That's a little bit more interesting as an example. So these are my sets, R, S, and T. So S union T. S union T is 1, 2, 3, 4, 5, 6, 7, 8. And R intersect S union T. What is the set R? 1, 4, 7, 10. Intersected with S union T. That's the numbers up to 8. What they have in common are just 1, 4, and 7. So R intersect S union T is 1, 4, and 7. What about R intersect S and R intersect T? Here's R, here's S. R intersect S is 1 and 7. R intersect T is just the number 4. So if I take R intersect S, union R intersect T, that's the set 1, 7, union the set 4, that's 1, 4, 7. And you see, these are equal. So in this example, R intersect S union T is the same as R intersect S union R intersect T. Now, in algebra, and in any math class above the sort of baby classes like calculus, you have to prove things. How do you know something is true? You give a proof. So let me give an example of a proof of one of the distributive laws. So let's give a proof that R intersect S union T equals R intersect S union R intersect T. So this set equals this set. That's what we have to prove. How do you prove that? You have to show that if something is an element of the set on the left, it's an element of the set on the right. And conversely, if every element of the set on the right is an element of the set on the left. So let X be an element on the set on the left, FR intersect S union T. So by the definition of intersection, this means X is in R and X is in S union T. And to be in the union of two sets means you're in one or the other of them, or both. So this means that either X is in R and X is in S, or X is in R and X is in T. Because if X is in S union T, it's in S or in T, or both. So this means X is in X intersect R, X intersect X. That means that either X is in R intersect S, or if X is in R and T, that means X is in R intersect T. And if X is in R intersect S or R intersect T, that means X is in the union of these two sets. So it follows that R intersect S union T is a subset of R intersect S union R intersect T. If an element is in this set, then it's in this set. So this is a subset of that. So we just proved the left side is contained in the right side. But you can actually write out this argument line for line in the opposite direction. Let me just do it quickly on the notes. Suppose that an element X is in R intersect S union R intersect T. Suppose this is true. This means that X, so just working backwards, is in either R intersect S or R intersect T. This means that either X is in R in S or X is in R in T. In both cases, X has to be in R and X is in either S or T, which means X is in R intersect S intersect T. So we get the opposite inclusion here. So this is an argument that you really need to spend some time at home thinking about. That's really the way it works. Any questions about this set theory that we've been doing? So, okay. There's one more property of sets which is important. Goes back hundreds of years. These are called De Morgan's laws. So the picture is you have some big set X, and sitting inside of X, you have sets S and T. So if S and T are subsets of a set X, then if we take S union T, let me just make some notation. So if S is contained in X, then what is called the complement of S in X is everything in X which is not in S. And we sometimes write that as S superscript C. This stands for complement. So XC means the complement of S in some universal set, some big set X that contains S. And De Morgan's laws, there are two of them. The first says that if I take the complement of S union T, that's the complement of S intersected with the complement of T, and S intersect T complement is the complement of S union the complement of T. So these statements are called De Morgan's laws. Let me give a proof of one of them. Give a proof of the first. So X, an element, is in S union T complement. What does that mean? That means X is not in S union T. The complement of this set is everything which is not in the set. So X is in the complement of S union T, means X is not in S union T. And to say it's not in the union means two things. X is not in S and X is not in T. Something fails to be in the union of two sets if it's missing from both of them. And this is the same as X not in S means X is an S complement. And X not in T means X is in T complement. So X is in this set and this set if and only if X is in the intersection of the two sets. And that's exactly De Morgan's first law. Any questions about this? So we say that, let's define this. A set is a collection of objects, just like, I don't know, a piggy bank is a set that contains money. And if you take all the money out of your piggy bank, you don't have any more money. The piggy bank is empty. So the set of all your money is, there's nothing there, it's empty. And that's actually an important set. What is called the empty set is the set that has no element in it, none. And it's denoted by a little circle with a slash through it, which is actually a letter in the Norwegian alphabet. Mathematicians had run out of Latin letters and Greek letters, and they needed more symbols, so someone picked this Norwegian letter. And that's the empty set. That's the set with nothing in it. And sets S and T are what is called disjoint if they have no elements in common, if the intersection is empty. So if we have some universe X and here's a set S and here's a set T, in this Venn diagram, these sets are disjoint because the intersection is empty. There's nothing in it. Right? The sets 1, 3, 5 and 2, 4, 6 are disjoint. And a family of sets or a set of sets let's call it, say, S sub I, indexed by a set I, that's what this notation means. Just a set of sets, a huge set, is pairwise disjoint if every two of them are disjoint. If Si intersect Sj is empty for all sets I and j with I different from j. So the sets 1, 2, 3, 4, 5, 6, 7, 8, 9 are pairwise disjoint. Of course, no two of them have any element in common. So suppose you have some set that consists of just the numbers 1 through 10. And let's say we divide it up into pieces like this. So let's say that S1 is the set 1, 2, 3, and 10. S2 is the set 4, 5, 8, and 9. And S3 is the set 6 and 7. So if you take the union of these three sets, that's the whole set X. Because every number in X is in at least one of these sets. But if you look at the intersections of these sets, like S1 intersect S2, that's empty. If you look at S1 intersect S3, that's empty. If you look at S2 intersect S3, that's empty. So the three sets, S1, S2, S3, are pairwise disjoint. So we have a very pretty picture here. We have on the one hand, X is the union of these three sets, but these three sets are pairwise disjoint. This is what is called a partition. A partition of the set X is a collection or a set of subsets of X, say S sub I in some set I. In this case, we have S sub I equals 1 to 2 and 3. That just means, this is just, let I be the set 1, 2, 3. I could write this as the partition, or look at the sets S sub I in this set. This is just a convenient notation. So this is a collection of subsets of X such that if I take the union of all of them, I get the whole set, and every pair of them have empty intersection or disjoint for I, J, and I different from J. That's what we call a partition of a set. Partitions of sets are very important. Okay. Any questions about this? Okay. I should say, just to make sure everything is, I defined the union of two sets. If you have three sets, this is all X, such that X is in any one of these sets. It's an SI for I equal 1 or 2 or 3 or more than 1. And if let I be a set and let S sub I be another set for each I in I, then we can define the union of all the sets S sub I This means the union of the sets Si for every I in this index set I. This is all X such that X is in at least one of these sets S sub I. Now, the examples of the sets I've written down have been all easy in the sense I can write them all down. But for example, we can let capital N be the set of all positive integers. I can't write them down. They're infinitely many, as we say. Or that R be the set of all real numbers. So a set S is finite if, well, it could be the empty set, that's finite, or there is a positive integer n such that we can enumerate the elements of S. S is equal to some element S1, S2, up to S sub n. These aren't necessarily distinct, but at any rate, this is finite list of elements, which is everything in the set S. And that's what finite means. And a set is infinite. Infinite means not finite if it is not finite. Okay. So far, I've just given a kind of vocabulary lesson. I'm defining these words that we use to describe properties of sets. In mathematics, we also need, this is very important, ways of proving statements. And a fundamental way to prove something in mathematics is using what is called the principle of mathematical induction. So the principle of mathematical induction says the following. Here's the simplest case. Let X be a set of integers. If the following two statements are true, if n naught is in X. So I'll translate this. So X contains the integer n naught. And if whenever an integer n is in X, that implies n plus 1, the next integer, is also an x. So this set X has a property that first it contains the number n naught, and second, if it contains some number n, some integer n, it contains the next successive integer n plus 1. So if both of these conditions are satisfied, then X contains all integers n greater than or equal to n naught. I mean, you can see why this is true. So suppose a set X has this property. So suppose n naught equals, say, the number 1 is in X. By this property 2, n naught plus 1, which is 2, is in X. By property 2 again, if 2 is in X, 2 plus 1 equals 3 is in X. By property 2 again, if 3 is in X, 3 plus 1, which is 4, is in X. By property 2, one more time, 4 in X means 4 plus 1 equals 5 is in X. And if we keep doing this, you see n is in X for every positive integer n, right, in this example. So this statement is the principle of mathematical induction. This is not something we prove. It's not, in fact, it can't be proven. It is one of the axioms in mathematics that we start with, this principle of mathematical induction. Let me give some examples of what we can prove using the principle of mathematical induction. Let's look at the sequence of odd integers. One, 3, 5, 7, 9, 11, 13, 15, and so on. So we have the first integer, 1. Then I want to look at the sum of the first 2, and then the sum of the first 3, sum of the first 4, and so forth. When I add up 1, well, that's just equal to 1. 1 plus 3 is 4. Add 5, you get 9. Add 7, you get 16. Add 9, you get 25, and so on. And we can notice 1 is 1 squared. 4 is 2 squared. 9 is 3 squared. 16 is 4 squared. And 25 is 5 squared. Let's keep going. This is fun. I add 11. 25 plus 11 is 36, which is 6 squared. I add 13. 36 plus 13 is 49, which is 7 squared. So you certainly see a pattern here. You get on the right-hand side the successive squares of the integers. 1 squared, 2 squared, 3 squared, 4 squared, and so on. And we might believe or hope to prove that this is, in fact, a true statement for all n. So we could say, well, maybe this is a theorem. The sum of the first n odd positive integers is always equal to n squared. And we can see this is true for 1, 2, 3, 4, 5, 6, 7, for any, certainly going from 1 to 7. So let me see if I can prove this theorem using mathematical induction. What does the theorem say in the case n equals 1? It says the sum of the first odd integer is the first odd integer squared. So the statement is true for n equal 1. What's the second thing we have to prove in mathematical induction? Assume the theorem is true for some positive integer n. That means if I take the sum of the first n odd integers, what's the nth odd integer? It's 2n minus 1. That's equal to n squared. Right? This is what is called the induction assumption or the induction hypothesis. Okay. What do we have to show? That this is true for n plus 1. That 1 plus 3 plus 5. Here, this is the nth odd integer. And then I add the n plus first odd integer. And I want to show that's equal to n plus 1 squared. Of course, this is 2n plus 2 minus 1. This is 2n plus 1. Okay. This is what I want to show. Is this true? Well, let's see. So here's the little proof of this statement. 1 plus 3 plus 5 up to 2n minus 1 plus 2n plus 1. That's the sum of the first n terms plus the n plus first term. But by the induction hypothesis, this is equal to n squared plus 2n plus 1. And they teach you in elementary school or somewhere that n squared plus 2n plus 1 is n plus 1 squared. So I just proved that if the theorem is true for the integer n, it's also true for the integer n plus 1. So we're done. That's the end of the proof.
Professor, can you move the page up a little bit?
Yep, there it is. Thank you.
Thanks.
Okay. Let's look at another example of something we can prove by mathematical induction. So if you're in computer science, you know a lot about binary sequences. A finite binary sequence is a sequence, a finite binary sequence, let's say of length n, is a sequence of n elements and numbers which are either 0 or 1. So 1, 1, 0 is a binary sequence of length 3. 0, 1, 0, 1, 1. This is a binary sequence of length what? I don't know, 4. No. So this binary sequence has length 4, 4, 4, 4, has length 19. This binary sequence has length 3. These are binary sequences. Let's see. What are the binary sequences of length 1? Well, there are only 2 of them, 0 and 1. 2 of them. What are the binary sequences of length 2? We have 0, 0, 0, 1, 1, 0, 1, 1. There's all the possibilities. There are 4 of them. What are the binary sequences of length 3? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, oops, yeah. 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. I think these are all there are. There are 8 of them. Of course, you can notice that 2 is 2 to the first power, 4 is 2 squared, and 8 is 2 cubed. So you might say, well, maybe that's a general rule. The number of binary sequences of length n is exactly 2 to the n. So that, in fact, is a theorem, but it needs a proof. So it's certainly true for n equal 1. That's what this example shows. The number of binary sequences of length 1 is 2 to the 1, or 2. So assume it's true for n. Assume the number of binary sequences of length n is 2 to the n. We want to count binary sequences of length n plus 1. But every binary sequence of length n plus 1 starts with the binary sequence of length n and then adds a digit, 0 or 1. So the number of binary sequences of length n plus 1 that end in a 0 is 2 to the n. The number of binary sequences that end in a 1 is 2 to the n. When you add, you get 2 times 2 to the n, or 2 to the n plus 1. So that is the argument. And again, it's written down in the notes, so it's easy to find and follow. It's important to observe there is a statement that also seems kind of obvious, that's equivalent to the principle of mathematical induction. So let's just make a certain remark. A non-empty set of, let's say, real numbers integers, fractions, positive, negative, zero, doesn't matter. Non-empty set of real numbers is said to be bounded below if there is a number L such that L is less than or equal to X for all, a non-empty set called the set X, for all elements X in the set capital X. So there aren't arbitrarily small numbers in the set X. You can have negative numbers, but like you could have all the numbers which are no smaller than minus a million. That set is bounded below. And the set X contains a smallest element if there exists an element X naught in X such that X naught is less than or equal to X for all X in X. So if a set contains the smallest element, it certainly is bounded below, but a set can be bounded below and not contain the smallest element. So for example, the set of real numbers, well, in calculus, we know is the open unit interval. It's all real numbers X, such that X is between 0 and 1, is bounded below by 0, but does not contain a smallest element, because 0 is not in the set. And no matter what element you pick in the set, like a third, there's always a smaller element, like a fourth. So this set is bounded below, but doesn't contain a smallest element. What is called the minimum principle says that this can't happen for sets of integers. So the minimum principle says that every set of integers that is bounded below contains a smallest element. So for example, every non-empty set of positive integers contains a smallest element. Because the positive integers are bounded below by minus 20. They're bounded below by 0. Actually bounded below by 1. So 1's not necessarily in the set, but it is bounded below by 1. And an important fact is that, so you can't prove the minimum principle either. This is an axiom in mathematics. So we have two axioms, the minimum principle and the principle of mathematical induction. And it turns out that they're equivalent. You don't have to assume them both. So the minimum principle and the principle of mathematical induction are equivalent. What that means is, if you assume the minimum principle, you can deduce the principle of mathematical induction. And if you assume the principle of mathematical induction, then you can prove the minimum principle. Okay. Well, so this is all like the basics. For any math class you take after calculus, you really need to understand these things and use them. And we use them a lot in algebra, the language of set theory and proving theorems, solving problems using mathematical induction. I will post the notes for what I did today on Blackboard, hopefully by tonight, and also a homework assignment for Monday. And that is what we're going to do.
Professor,